The last slide reminded us about the basic equation for exponential functions. The exponent is going to keep changing, the base is a constant number, and we allow a constant multiplier out front also. So they do say that a and b are constants. They are not variables. Just the x and the y are variables. And we have a few other restrictions. Now, if we're multiplying by this, there is one number that if we put it in for a, if we allow a to be that number to start with, then the whole function, we can just forget the rest of the function. And you probably realize this means that a can't be 0. Because if we say a is our constant multiplier, and our constant multiplier is 0, then the whole function just turns into a big fat 0. So a can't be 0. There are a couple of numbers that b is not allowed to equal. Now, it's going to be a constant. We can pick a number that's going to be fixed and we'll raise that number to all different kinds of powers. But there are some bases that if we pick them and raise them to a power, nothing happens. So b cannot equal, well, b can't equal 0 either. Because if we take 0 to any power except 0, which is undefined, 0 to the first is going to come out the same as 0 to the 7th, is going to come out to the same as 0 to the negative 12th. So b can't equal 0. And there's another base that's pretty useless. Because no matter what what exponent you put on this base, you get the same answer back. So you've probably figured out that b can't equal 1. Because 1 to the first, 1 to the 7th, 1 to the negative 12th, they all come out to be 1. So we can't let b be 1. We pick a really simple example. Say y equals, I'm just going to let 1 times 2 to the x. So when x is 0, we would have 2 to the 0 power, which is 1. When x is 1, we'd have 2 to the first power, which is 2. X is 3, we'd have 2 to the third power, which is 8. X is negative 1, we'd have 2 to the negative 1 power, which is a half. When x is negative 2, we'd have 2 to the negative 2 power, which is a fourth. And I think you get the idea here. Now, when we did 2 to the third power, that meant 2 times 2 times 2. If we had done y equals 2 to the fifth power, let x be 5, which I'm not going to try to fit on this thing, we would have 2 times 2 times 2 times 2 times 2, which does happen to come out to 32. We are constantly multiplying by 2. So 2 is our constant multiplier. And because we are multiplying always by a number that's bigger than 1, the graph keeps getting larger. And this is the exponential growth model, which you looked at in the last lesson also. So in this case, 2 would be the growth factor. Because it's what is being multiplied all the time. If we have y equals, yeah, I wanted a different color here. Doesn't seem to have a different color. If we had y equals -2 to the x. So if we let x be 0, -2 to the 0 is 1. If x is 1, -2 to the first power is -1. If x is 2, -2 to the second power is +4. If x is 3, we'd be taking -2 to the third power. If x is 4, we'd be taking the fourth power on -2, which is +16. Well, this is causing a problem here. This thing is zinging back and forth. And so our graph is doing something like this. This is not an exponential graph. It doesn't behave itself. It's constantly flipping back and forth between a positive answer and a negative answer. And this is going to keep increasing. Over here, it will keep decreasing. So we have no negative bases. We are not going to allow our base number to be a negative number. So b has got to be greater than 0. Because we already said b wasn't equal to 0. So that's another restriction, another what they call constraint. We have these restrictions right here. These are sometimes called constraints. Something is constrained, it's got limits on it, boundaries. Just don't try taking a negative base for our exponential function here. Let's look at one more case, please. Don't need this many values really, but I get carried away sometimes. How about y equals 1/2 to the x power? Now that's not negative, and it's not 0, and it's not 1. So this should work. If x equals 0, 1/2 to the 0 power is still 1. If x equals 1, I'm going to take a half to the first power. So that's a half. If x equals 2, we're going to be squaring a half. Oh, we're down to a fourth now. If x equals -1, we have 1/2 to the -1 power, but the -1 power means reciprocal. So that actually comes out to 2. If our exponent is -2, well, that'll be the reciprocal on 1/2 squared, which is the reciprocal of 1/4. If x equals -4, we got 1/2 to the -4 power. That is the reciprocal raised to the 4th power. That'd be 16. So our dot would be up here somewhere. And our graph is doing this. And as you reviewed in the last lesson with Mrs. Milburn, this is exponential decay. And it happens when the base is in between 0 and 1. If the base is some proper fraction. We know we can't use 1 as a base. We know that we can't use anything that's 0 or negative as a base, but we can use proper fractions as the base. And when we do that, our constant multiplier is going to be a fraction. So our growth factor is a fraction. Which means that it's not growing, it's actually shrinking. And hopefully, lots of people think that growth is great. Growth of population is great until there's not enough food supply. And they try to slow down the growth. We know what growth in viruses and infections does, and it's hard to slow down that growth. Hopefully, once the vaccines come in and enough of us get the dose, don't know how long it's good for, but we will be able to bring the amount of illnesses and have it be a decay model rather than a growth model. So those are some basics of exponential functions. For growth, we have to have a constant multiplier that's greater than 1. The base has got to be greater than 1. For exponential decay, the base has to be a proper fraction between 0 and 1, and we can't use any negative bases.